So at this point, I would just like to remind you that you should have received an announcement of the midterm arrangement. The most important thing is that we start the exam smoothly. Once it started, then everything will go smoothly, I believe. So I would like to remind you that please get in on Thursday earlier. Work with the TA to set up one webcam. I don't need two things like that. I don't like this kind of, it's like so-called police against robberies idea. I trust that you will do whatever a student should do. Okay, so only one webcam. So the TA will work with you to set it up. And then more importantly, please go into the right breakout room by yourself. My IT skills do not allow me to, or the time, to pre-assign you and so on, okay? You know who you are, right? You know your last name. So try, come in and then select the right breakout room. If you get in the right room, then one TA will only look after something like 18 to 20 students, and that is easy to manage. Work with the TA, set it up, and hopefully by 12:30, we can set up everything, and then I will distribute the exam paper. All right, please cooperate, please help. So let us continue. So we talk about Einstein's work, AB coefficient. I really want you to appreciate Einstein's physics. No, not necessarily complicated, but really insightful. And with his result, A related to B by a factor, suddenly we can come back to quantum mechanics and has a expression that we can work on to get at the spontaneous emission rate. This page is extra with a box. It is just a way to understand why I flip the A. A has 1 over time unit. So I flip the A, it gives me a time, a lifetime. This argument is also used in nuclear physics, in which you have a collection of decaying nuclei. It is probabilistic. You don't know which one will decay and which one will not. But as a statistical idea, we know that the number of nucleus up there not decaying will drop in time exponentially. Okay, so here's the same argument. If at a time t I have n2t up there in the excited state, because per atom per unit time it will come down. So dn2 dt is a dropping, so negative. This is per atom per unit time, so time is already taken care, the unit is right. But it is per atom. If I have n2 atom up there, therefore this is the decaying equation for the number of atoms in the excited state. Everybody can do this, can solve this. Divide this to this side, dt go to the other side, integration, so you pick up log and then do an exponential. Okay, so therefore you have this. So therefore it is decaying. Okay, so minus AT means 1/A is a tau. So this is minus T/tau. Okay, you don't need to learn it again in nuclear physics. So this is the same argument. Now, we have to think a little bit more in order to define the lifetime of an excited state. So I have an excited state called number 2. If there's only one state to go in, 1 down there, then we already got the expression, okay? Because A is given by that, 1 over A, you flip it, it's already given by that, okay? Provided that state 2 has only one state to go in. But in generally, in an atom, a high excited state could go to various states with lower energy, okay? Some will be more readily occurring, or some will be occurring in a smaller probability. But for this excited state, there are many channels. This expression is assuming only one state to declare 2. So this is the answer, something that we can calculate. This week, sample question number 20, the TA will plug all the numbers in and then show you what is the excited state of hydrogen 2p. The lifetime of hydrogen 2p, okay? Because it has only one S to go to. And this is exactly the situation, okay? So therefore, the TA has to calculate this difference and then this integral, which is a vector, and then take a cube and so on, take a square and so on, and get a number, really get a number, okay? And then we have a byproduct. If you have an excited state with nowhere to go via electric dipole mechanism, then it will have a longer lifetime. All right, now that is called metastable state, turns out to be useful in some applications. For example, in designing laser. Just one more thing, let me reiterate. The lifetime of a state is related to the spontaneous emission, not stimulated emission. You stimulate it, that's another thing that it is interesting, but it is not how the lifetime of an excited state is defined. It is defined as leaving it up there. Don't do anything to it. It will come down, okay? This extra page is again an optional page just to point to you some recent research area. There's a field called ribbon state or ribbon atoms. It is related to exciting an electron in an atom to very high excited state. For example, n equals 30. Wow, that is very far away from the low-lying things, okay? But still, experimentalists can do that. The interesting thing is that this particular state, for example, 30s, okay? You're excited to n equals 30 and the L equals 0, S, okay? Or P, 30p, all right? Now, if you just think about hydrogen, you take hydrogen's formula. When n is 30 or 40, the distance of that orbit from the nucleus maybe is 10 to the minus 7 meter or so, or 8. Okay, now 1 angstrom, the ground state, is something like 10 to the minus 10 meter. So suddenly it's 100 times away, or even 1,000 times away when n is 50. So it is very loosely bound. Another way to say that is if I add 10 to the minus 5 eV, that will take the electron away. So it's a very delicate and challenging experiment to do. Nonetheless, that can be done. The interesting thing is that because the behavior is very hydrogen-like, therefore the physics is very clean. You take one electron very in higher orbit, all the others forming a core. So it looks like even it's not hydrogen, this particular state is very hydrogen-like. So very simple physics, kind of, so to speak. And a very interesting thing is that although it's highly excited state, you may think omega cube is very big, therefore very short lifetime. If you think about the omega cube factor, it is true. But we still have a matrix element, a distance matrix element. If you use the ground state as the lower one and n equal 50, p as the upper one, they live in very different space. Therefore, that spatial integral can be very small, okay? So that will make the tau not too short for experimentalists to probe this ribbon atom. Very interesting thing in recent years. So for those who are interested, I would point you to a 30 pages e-book. We subscribe it in the library, the physics department pay for that. You can look up ribbon physics. It is Institute of Physics in the United Kingdom, one of the many e-books from this Institute of Physics. Only 28 pages, very easy to read. So finally, more formally, from one excited state, there are many lower states that the atom could decay spontaneously. In this case, our dynamical equation dn2 dt formulae would have many terms. For example, 2 to 1 prime is this term. Okay, so similarly, you could have many possible lower states. Of course, you can solve it like the previous exercise. Therefore, tau 2 is given by 1 over all this rate, transition rate, spontaneous emission rate. And of course, when you have that many, one of them dominate. Well, if that is the case, life is easy. One is much bigger than the other, okay? Or else, if you want to flip the thing, 1 over tau of the excited state 2, it will be all the transition rate summed together. And if you defined each transition rate to be its own 1 over tau 2, 1 prime, etc., maybe one of them dominates. That is the most readily occurring. Okay, so this is the general definition for a lifetime of an excited state, when there are more than one lowest energy states to decay into. So now we know the idea about excited states, lifetime. Just give you some ballpark numbers. For example, the TA this week will show you hydrogen 2p. There's one state to go down, but this is allowed transition. Therefore, the rate is not small, and therefore the lifetime is short. Okay, so typically it's something like 10 to the minus 9 second. That is the lifetime of an excited state with allowed electric dipole mechanism to go down. In contrast, there are some longer lifetime states, metastable state, that could take on a tau as long as something like 10 to the minus 3 seconds. These are excited states. So with this background, we could start our final part of this module. This is a brief introduction to the design of laser. It is an application of stimulated emission, but we can only give you a brief introduction for the following reason. We have not treated stimulated emission fully in quantum mechanics. We haven't quantized the field, we haven't done any quantum optics. Therefore, you still have no mathematical background about the property of the emitted light. For example, all the things about phase coherence, the stimulated light, and the stimulated emitted photon, they have identical properties, things like that. That has to do with a proper treatment of the quantum mechanics of stimulated emission. Nonetheless, we have some idea about lifetime, and therefore that will allow us to appreciate the experimentalist design on forming lasers. So first of all, what is laser? Laser is the shorthand of light amplification by the stimulated emission of radiation. This radiation means light, EM waves, okay? So all this work put together is laser. So when you have lasers, it's rather funny, okay, with a plural, but you know that nowadays becomes a daily life word. So really, people use lasers. So the idea is the following: if we can put more atoms up here than down there, therefore maybe if there is some light of the right frequency coming in, that could stimulate atoms to come down. Therefore, you will have some extra light coming out. But that's true. So that is to take advantage of stimulated emission. But just to remind you one piece of physics I already emphasized, if it is under thermal equilibrium, you cannot get this situation because you always have this. Okay. Therefore, under ordinary situation, room temperature, even 350K, 400K, you heat up the sample a little bit, you put in light into it. Usually a material is not a lasing material, it is an absorber of light. Why? You have more atoms down here than up there. So you give in more here, absorb up, okay? Of course, there will be some stimulated emission occurring as well, but more atoms here, meaning absorption is more than emission. Therefore, if you want to explore this idea, you need to put more atoms up there than down there, N2 bigger than N1. That is unnatural. This is called population inversion. That is the technical jargon. But this substance, this material cannot be in thermal equilibrium. It is out of equilibrium. It also means the following. We need to invent some ways to do it. And that is at the heart of the early design of laser systems. So just to make the point clearly, usually we have absorbing situation. This is the ordinary situation. You have more atoms in the ground state, a lower one than in the higher state. Okay, so this two, dark one is in the higher state, open circle is in the lower state. You see more open circle than the dark circle. Okay, and then you shine some incident light a certain distance, it drops. absorber. Okay, this is an absorbing material. In fact, in your EM course, say Griffin's textbook, there is something called the absorption coefficient, alpha. Okay, so if you make use of a stimulated absorption, emission, you know there's one term that is absorbing. Down there, they will absorb. One term that is putting in energy into the beam, stimulated emission, but because N1 is bigger than N2, if your material is at equilibrium, 300 K, for example, it is an absorbing media, you have this decaying behavior in the intensity that defines the absorption coefficient, okay? Now, that also means the following, and other appreciation of quantum mechanics. We can calculate the absorption coefficient by quantum mechanics by using the formula that we got for the transition rate. That is part of solid state physics. But that's what not we want to discuss here. We want gain medium or active medium or amplifying medium. Now, these are all the words used for lasing materials. Okay, so it means the following: somehow we find some way to achieve population inversion that is unnatural, that will not last long. Okay, and then you see more dark dots than open circles, and when you shine in light, then you will get a, this is smaller amplitude, this is bigger, okay? You will get more light out. Mathematically, it means it's not exponentially decreasing in intensity along the gain medium. Instead, it is growing. And this is the growing factor. But in order to get this, you need population inversion. And that leads us to two typical designs that we would like to introduce. The first design is so-called three-level design. Sometimes this is a simplified version. Very often, we have 1, 2, 3 levels. Very often, for example, level number 3 up there could be a group of nearby levels, but still it is in the family of 3-level design. This is the first laser coming out, giving out red color. Before that, the first lasing system was invented by Charles Tans in 1954, but it's not in the optical range. It's not in the colored things that we can see, but in the microwave range. It's called MESA. But the first that get into the optical range is this one. I think it's done in Bell Lab, in the Hughes Research Lab. Okay? So it is ruby laser. So let me tell you what is ruby. It is basically, what is this? Aluminum oxide. And then there are some defects or impurities in it. Some chromium 3+ ions. The impurity is not very high level, 1 in 1,000, but it's already quite a number. And it all depends on the energy level of this chromium ions. So let me introduce the idea of achieving population inversion in this 3-level system. First, back in the equilibrium situation, you usually have more atoms down there than up there, especially if it is optical. For example, if this is red, okay, red is something like 1.6 eV in terms of electron volt. Room temperature is (1 over 40 eV), okay, or 0.025 eV about. So this is some numbers that you also want to keep them in mind, especially in your thermal physics course. So therefore, with this, room temperature things, you can hardly thermal excite anything up there. That is to say, the ratio is tiny, tiny, tiny. All right. That's why I don't even draw anything up there. So this is the equilibrium situation. And then you need a process called pumping. In laser design, find some way. Usually you use some light source, shine on it, okay? In this case, a common method is to shine in a green light source. Of course, not another laser, just green light. In this case, that can populate not only level 2, but also level 3. So you have fewer atoms here, and then you have this, okay? Nonetheless, there's still an appreciable number here. So basically, you can do it by pumping and achieve something like 1/3 down there, 1/3 in the middle, 1/3 up there, because of the dynamical equilibrium. Okay, lambda 1, 2 is lambda 2, 1. So go up there, you come down, okay, and then you achieve some equilibrium. So therefore, we need to choose the property of level 2. If this is metastable, a longer lifetime, and this is a short lifetime state, this come down, those here at level 3 come down quickly with a fast decay to level 2. So a short while after pumping, you achieve more atoms in 2 than in 1. Okay, and therefore you can use stimulation to start a stimulated emission process for this more atoms here to come down, and therefore you will get some very strong and nicely so-called time and spatial coherent outcoming light. But that lasts as long as N2 is greater than N1. Once that is not true, the action will end. So it is a pulse. And then you have to pump it up again and then do it again, okay? In short pulse. So 3-level system can give us short pulses, well, rather strong sometimes, okay? So this is the idea. A disadvantage of 3-level system, I mentioned it here just to lead to the next design, is that the lasing process between level 2 and level 1 relying on the ground state level 1. But usually we have more atoms in the ground state than in all the other states. Therefore, it is hard to keep population inversion going. That is to say, if we want continuous operation, that cannot be done. Later on, we will talk about a 4-level design, and that will give us so-called continuous wave operation. So this is how it goes. I mean, this is the same thing as this. This is the real picture. So basically, the pumping is done by shining green light by this fresh lamp. Okay, and inside there we have some chromium ion that has these levels 1, 2, 3, and at the end we get some red lasing light out. There are some very technical thing called you have two sides with mirrors. One is perfectly reflecting, one is 99% reflecting, and there is that 0.something% that can come out as our laser light. The other light are reflected back, so to stimulate more emission and so on. And this can be designed, the separation, to select a very sharply, very sharp wavelength and frequency, that is to say. So to put the idea together, we have 3 levels. We have chromium 3+ ions, and then we have this level 3, pump it up, come down fast, and then this is the lasing levels. Stimulated emission come out with this wavelength, red. Put the whole thing together, this is the typical 3-level design. Pumping, quick, fast decay, populate to achieve population inversion, and lasing come out, okay? So the 3-level design, I already hinted at, it is a pulse. Usually it's not a very effective design, but nonetheless it worked. Ruby laser is very special because somehow chromium 3+ ions have that special alignment of the 1, 2, 3 levels so that it works. But not so many systems can be found. So the idea now is to avoid using the ground state, and maybe it's easier to achieve population inversion. That leads us to 4-level systems. So the idea is summarized in one single diagram. So we have ground state, usually this is heavily populated. Then we have a group of things called 4. There's a pumping process, take atoms out from ground state to a high level, and we need some fast decay to 3, allow the transitions, all those things. And then we'll populate 3, and 3 and 2 is the lasing levels. So this is the light that comes out by stimulated emission. But 2 is also readily decaying to the ground state. So whatever atoms that come down here, it will quickly leave level 2 and come down to the ground state. Thereby, it is possible to continuously populate 3 with more atoms than 2. Once this come down, fast decay back to the ground state to sweep away the atoms accumulated in 2. So to keep 2 rather clean, and 3 there can continuously give us stimulated emitted light. So that is the 4-level system idea. So in a divided process diagram, again, at equilibrium, atoms are in the ground state, usually nothing there. You need some way to pump it, but whatever you do, basically what you can do is you have about the same numbers, okay? But if this is fast decay to 3, then you will have many atoms in 3. And this is fast decay back to the ground state. You clean up this thing, and you choose this level 3 to be a longer lifetime, metastable. Therefore, you achieve population inversion between 3 and 2. And now you're ready to get lasing action here. Once you get that, the atoms in 2 will come down quickly so as to keep this place rather empty. Okay, so that's the idea. Now, that is the idea. The way to get the first continuous wave laser working is not that trivial. It is the famous gas laser using helium-neon mixture. So two gases, inert gases at the right ratio, and you need also to control the so-called relative pressure. So how many of them inside your gas tube? Now, we have some background to understand this design. So let's use our helium atom knowledge. So the mixture is about 85% helium, but helium is not the lasing materials. Neon atom is the lasing materials. So helium here is to do the pumping, okay? But in a very ingenious way, I would say, innovative way. So the idea is the following. We need to excite the helium atom to some low-lying excited state. That is to say, to give some extra energy to the helium atom, so that by collision with neon atom, the helium atom could give out the energy and excite the neon atom to level 3. Okay, now that is the big picture. Let's see how it goes. So the whole thing is very clever, very clever. Okay, so we will have to use some so-called electric discharge, meaning using some electrode, you have some energetic electrons that will collide with the helium atoms to excite it to excited states. So let's use our knowledge. So maybe 2 weeks ago, we discussed helium excited states, okay, for the purpose of the exchange energy, direct Coulomb, things like that, okay, so that you have some idea. And also the anti-symmetric requirement of 2 electron wave functions, okay? Nonetheless, at that time, we have a good discussion. We know that the excited state, if I put 1 electron in the ground state, which is 1s2, I take only 1 electron. So I leave one in 1s, another in 2s. There are 2 possibilities. There's a triple state, s equals 1. There's a singlet state, s equals 0. And we also argue that, in fact, due to the Coulomb interaction, triple state has a lower energy because the 2 electrons tend to avoid each other in the spatial part, and then the singlet state has a slightly higher energy level. So let us draw this energy out. So this is ground state. I set it as 0 eV. It doesn't matter, it's relatively speaking. So this is this one, okay? Now, if I put it into this, there are 2 choices. There's a triple state that is about 20 eV, and there is a singlet state that is this one, s equals 0, 2s plus 1 is 1. That is about 20.6 eV above the ground state. So now the electrons or electric discharge will collide. The electron will collide with helium to excite them to these 2 excited states, okay? Both will be excited, and then the next picture will focus on this excited helium atoms. Now, the nice thing is that now let's use this chapter's knowledge. All these are L equals 0. Electric dipole requires a selection rule, which is delta L is plus minus 1. Okay, so therefore, optically, these are not allowed. Therefore, these are relatively long-living helium excited state. That is to say, they can hold this 20 eV energy for a longer time to collide with neon atoms. Okay, now you see a lot of quantum mechanics going into this kind of design of the first good lasers, continuous running. Now let's look at neon atom. The ground state is this. We talk about the periodic table. Now, when ground state neon collide with helium excited atoms, there are 20 eV to give to the neon atom. Now we can consider excited state of neon. For example, taking 1 electrons from the 6 electrons in 2p and bring it up to some higher level. I call it NL. That could be 3s, 3p, 4s, things like that. Okay. In particular, there is one 5s1, a very highly excited. Okay, that is about 20.6 eV above neon's own ground state. So perfect. First excite the helium atom, but it is just a catalyst. The helium atoms play no role in laser. Okay, now it collides with the neon and give up that 20.6 eV to excite the neon atom to this excited state, and this is level 3. So this is the picture to make sense out of it. This side is pumping, is using helium atom. So our 4-level diagram is schematic, Practically, it's a different thing, but you still can put it into that diagram. So this is pumping, and now the collision between helium atom and the neon atom. So helium excited collide with neon, helium de-excited give up 20.6 eV, put neon into an excited state. It turns out that this is exactly about the same energy above neon's own ground state. Through collision, neon is excited to this level 3. All right. Now, there's a level 2 in the neon excited state. We have been using 5s1 here, but it can go down to 3p1. Now this S to P is delta L is a 1. Therefore, that is, electric dipole allowed. And that is the level 2. So this is the light that comes out. I think it's red, okay? And then we also mentioned that this too has to clean up quickly. And there are several states that this can go to. For example, from 3p to 3s is allowed. Therefore, once neon atom comes to here, it will quickly go down there and then decay back to the ground state, and then waiting for another helium atom to collide. Okay, now, many quantum mechanics gets into this design, especially multi-electron atom physics. So sometimes you see some very simple description in textbooks. Okay, so this is a simplified version. Nonetheless, I hope that you appreciate a lot of quantum mechanics goes in. Lastly, I would like to briefly talk about semiconductor lasers, because nowadays you have, for example, this disc player, CD disc player, and then inside there you have a semiconductor laser, and you have this laser pointer. It's not big, it's so small. It is semiconductor stuff inside there. This is gas laser, it's like a big tube, okay? This thing is like a big tube. So what happened in a semiconductor laser? Basically, it's the same idea. When you use quantum mechanics to understand the electrons in a solid, after solving the Schrödinger equation, we will find there are many allowed energies in a range of energy, and then there's a range without any allowed energy. That's to say, there's no energy eigenvalues there. Well, that's natural, right? I mean, hydrogen. If you just blindly point at the energy, there's no state there, right? They're discrete. So in a solid, it's more or less like this, but there's a range full of eigenvalues, a range with no eigenvalues, another range full of eigenvalues, and so on. They are called bands, energy bands. Now you fill in the electrons. For semiconductor, up to a certain band, it's completely filled. I call it full. And then any higher states are completely empty. Technically, the last filled band is called the valence band. This first empty band is called the conduction band. The not allowed region in between is called the band gap. So this is a semiconductor. So how to get laser out of a semiconductor? Give me 3 more minutes. So we need to do something called making it dirty. Now it's a very funny thing. Semiconductor, silicon, is the purest material that human made on Earth. Okay, now nowadays, you know, there's a shortage of semiconductor wafer. That's why even Tesla cannot produce more cars than they wanted. A computer company, phone company has difficulty producing a new version of their phones due to semiconductor thing. We started from sand on the beach, okay? Then you purify them. You make it as pure as possible. And that is what is now in shortage. Then you make it dirty again. That is called doping. So how to make it dirty intentionally? You put in impurity, but you know, a very costly machine. So the idea is the following. In a semiconductor, this is completely filled with electron. This is completely empty. But now, intentionally, I put a few electrons in an otherwise pure semiconductor. That is called doping. This way of doping is called negative doping. I put in more electrons. That's why it's called N-dop, N-type. There's another way to do it. This is full. Now I take away a few electrons. So these empty circles are meant to represent missing electrons. This is called positively doped. You miss some negative charge, the whole thing is positive. It is called P-type. Okay? And now you put them together. So you have 2 pieces, put them together. So this, you have some electrons up there. You have a few missing electrons down there. You let them meet. Perfect. The electron up there, high in energy, uncomfortable, seeing some empty state with low energy, good, come down. Come down, light comes out, you get LED, light emitting diode or light emitting devices, okay? If you design it in a better way, you will get laser, and that is how semiconductor laser is formed. So final remark. In this module, actually, we did a little piece of quantum mechanics formulae. We developed time-dependent perturbation theory. We also developed the perturbation form of how the electron in an atom interact with the light part. That is the H prime that we write down. We only focus on electric dipole mechanism. Then we applied that formula. We got a lot of things. we focus on atoms, we get the selection rules, we get the right selection on the frequency, we get the transition rate, we even get the spontaneous emission today. And we understand lifetime of a excited state, we understand metastable state, we have the basis to go further on quantum optics and lasers. What we discussed work for atoms, work for molecules, and work for solids, work for disordered materials, or other things. This is a big topic called optical properties of matter. That is a huge literature of this. But I think you have the background to go into any one of these areas. This is the last page. I give you a few references. For those who like formulas, not much application. These are the standard quantum mechanics books. But I encourage you to be more practical. For example, Yarif, a very famous Caltech professor, for his work in quantum optics, he wrote a undergraduate textbook on theory and application of quantum mechanics, very applied side viewpoints. And if you want to know more about lasers, same over, Yarif, quantum electronics. I just look at it. Out of 24 chapters, you know 13 of them, so you are halfway through. You don't know that, but you know, don't be afraid. Just take it and cut in the middle, read the other half, you get all the things. And for those who like atomic physics, AMO is now a big field. Atoms, molecules, and optical physics. So if you want to know more about atomic physics, then there is a very good book by Christopher Foote, Atomic Physics. I think it is at the year 4 or beginning master level discussion. I think you know about 40% of the book, or 50%, half of it is okay. It's easy reading. Another year 3 level book is by Max Fox, A Student Guide to Atomic Physics. I think you know 80% of the book. There are chapters on lasers, laser cooling of atoms, co-atoms. That is something what Professor Wang Dajun is working in his lab. That is something that I haven't covered. Usually it will be covered in statistical mechanics as a chapter on Bose-Einstein condensation. So we have a 2 weeks module on this very fascinating topic, okay? So first day we will have the midterm. Please come in earlier. Then next week, we will start a new module on molecules, how atoms come together and tend to bind to form something else, okay? So long for now. I will stay for your questions.